It's good.
Ready?
Okay. Welcome everyone to the final short science talk session. I'm the chair. I'm Elliot, so I'm a PhD student from Birmingham. So as before, we've got 6 scheduled talks, about 15 minutes each, and this will take us to lunch. And first up, we have Kendall Ackley with identifying galactic ultra-compact binaries with GOAT.
Okay. So thank you, everybody. I just wanted to thank the conference meeting organizers for allowing me to give a talk. And what I wanted to talk about today was introducing a dedicated optical instrument, which is gravitational optical transient observer, which is dedicated for looking for gravitational encounters. And so it's really nice to be here. I actually started my first scientific foray in LISA a long time ago when I was an undergrad, so it's really nice to be back. And but I wanted to kind of showcase this instrument and see what the possibilities look like for using it for LISA science, as well as an update about what we're currently doing and what our plans are for the future. So the GoTo collaboration is actually a very large collaboration. This one has 50 members with institutes all around the world, Australia, all throughout the UK, as well as Thailand. So just the motivation for the telescope project, it is specifically designed for rapid follow-up of gravitational events. The philosophy behind it is that it's cost-effective, it's scalable, it's adaptable, and we can always adapt and change our needs to whatever the gravitational signal is that arrives. So if we're looking for binary black hole events or binary neutron star events, we can actually adapt our observing strategy to sort of maximize the scientific output. And so you can see here briefly is that we have the telescope on a single mount. We have 8 telescope systems that will actually track. And then we have 2 sets of these currently in operation, which I'll discuss, currently in operation in the Northern Hemisphere in Palma. And so there's always a trade-off between cadence, area, and flux. And so what we've maximized is the area side. So we capture as much of the sky as fast as possible, where the GoTo instruments will be approximately with both sets about 8 square degrees in extent. So just a little bit more about the prototype system. So there's actually a couple of different setups here. So the prototype system, we're calling it from 2017 to 2020, where first light was taken in June of 2017. It consisted of 4 telescopes of 40 centimeter f2.5 unit telescopes, or UTs. It was about 8,000 by 6,000 pixels with a pixel scale of 1.2x pixel, where we had an FLI microline camera, which is about 50 megapixels in extent. And we have a 5-slot filter wheel, but we're primarily observing in this L band, which you can see here. This L band encompasses a very wide swath of the filter band. So basically, so we can observe as much of the sky as possible without necessarily having to rely on color information. So things like kilonovae, they might be red or blue, but we should be able to capture the full extent of that. And in the L band, we can get down to about 19.8 magnitudes in the 6 seconds. So here we can see roughly the field of view of a single UT, which entirely encompasses in the. If you want to read more about the prototype system, the paper's out from Snake's volume. Okay, so more about the system itself. So you can see here the 4 UT, or the 4 unit telescope prototype that was installed, and this was a photo from 2018. We just had 4 telescopes at that time. We're located in La Palma, right about here, which is at the Warwick site, right across the street of Warwick 1 meter, which is dedicated for Warwick follow-up and Warwick science. You can also see we're across the road from the Liverpool telescope, where we can trigger the spectrograph on there, as well as the knot, which we can trigger, as well as CTA for multi-messenger coordinated observing. And so we get to communicate with these facilities quite often to help to participate in this gravitational wave science. In 2020, we actually upgraded to our 8-unit telescope prototype. And this is what we were operating with for the second half of the LIGO Virgo Kagra 03B run, where that's up until, I guess, things changed and we switched into our full design. But just for the most part, GoTo operates in the sky survey mode, which is we need to collect as many template images as possible so that we can do our image subtraction to find these very fast transients associated with these repetition rate images. So we operate in sky survey mode most of the time. It's fully autonomous, and we use a just-in-time coordinated scheduling where we receive an alert and then we automatically do some probabilistic calculations and then start to target the sky map area. And of course, we have plenty of synergies with secondary science cases. Blind kilonova research is, we look for luminous transients, so we actually have dedicated science AGNs, tau disruption events. We've had several undergraduate projects doing AGN cross-map searches and TDE searches with modeling with Daniel Price at Monash University. We also do long-term monitoring because we revisit the same fields every night, and we also have multi-band coordinated observing with other facilities in the works on the Palma. Okay, so this is just the general operations that we had for this time period from March 2019 to August 2020. You can see here the scale of the number of tiles we have observed. So we observed the full northern hemisphere. You can see a couple of tiles here. In particular, these are highlighted T2204 and T2407. These were two particularly interesting targets where we just watched M31 for over 50 times that year, as well as a transient AT2019 PJ, which we also targeted. So we divide the sky up into a set of fixed tile grids, and then we repeatedly revisit these every night so we can create templates and also just and so when we receive a gravitational wave alert, we map it onto the sky and start targeting in that sense. So for O3A, we targeted 32 events. That was written up by Ben Gomberts, who's here in Birmingham. We're working now on the O3B catalog, which we triggered for 20 events. That's being finalized. We also, in the absence of LIGO events, we also trigger on gamma ray burst events. So we follow actually Fermi, Swift, and we use those as proxies, especially the Fermi, which are wide field of use. We actually use those proxies for LIGO follow-up. And this was published by Long et al. And of course, we also have serendipitous transients, such as this event, which you can see here in blue. We were able to observe it, send it off to the Liverpool telescope, and then observed it with SPRAT to get this orange spectrum here. Okay. So since then, in June of 2021, we actually fully dismantled. We actually had the second dome installed completely. So you can see this is the new hardware here. So we're using the ASA, which is an Austrian astrograph company, who has built this, and so we replaced the mount, and we have 8 new telescopes here, and this is the first image from that. So we had major performance upgrades, a step upgrade where we have better mount stability. We're not as sensitive to wind shake on the instrument. Off-axis point spread function is more stable. Basically, all new hardware. We drastically improved our slew speeds by a factor of 2, and we increased our survey volume rate also by a factor of 2. So we're able to quickly and rapidly scan these skies to steps. And then since then, in November, this was the prototype instrument. So we completely dismantled it here and replaced it with the same hardware that we had in the second. So right now, we're currently operating with 16 telescopes in total, which is about 80 square degrees in extent. And we're calling this now no longer the prototype, but the full design for the GoTo North. And some of the technical upgrades that we have since the prototype is we have a full custom in-house pipeline that monitors each of the data products as it's coming in. We had a bit of interesting communication with the Vera Rubin Observatory where we actually used the LSST stack on the data. And it's, I think it's actually really interesting how they plan to do their photometry, which they have this sphere, and then you just back your tiles onto the sphere, so you can just take pictures in any place and get the photometry in place no matter where you're pointing. So we tried that, and we got to contribute to their studies, I suppose. We also have different classifications, so we're making use of some AI. So we're using a real bogus classification to identify junk from actual transient sources using a Bayesian CNN. We also have imbalanced light curves. So if your light curve is not properly sampled, evenly sampled, we're making use of a recurrent neural network to improve light curve classifications. And we also have improved Marshall's brokers, contextual agents here, so we can read out an event as it comes in. So what you see here is one particular event. This was related to one of the LIGO Virgo events. I think it was September of 2019. Here we have an event goes off. It's a bit tiny to see. We have an event go off. It gets picked up. And we just have a button on here to just trigger Sprat. So we say, okay, we have an agreement with a certain amount of time. This one looks good to trigger. We trigger with Sprat and we get a spectrum immediately. And then, as you can see there, if it is interesting, you can then report it automatically to the transient name server to let other people know about it. Okay. All right, so now the full design. So what are our plans for GoTo in the future? So the full design is that while we have a full 16 telescope system in La Palma, we're planning on breaking ground any second now at Siding Spring Observatory in Australia. So we're going to have basically 2 nodes, so 32 telescopes in total, and we're going to fill these large longitudinal gaps for gravitational follow-up, mainly the southern hemisphere, which is very much underutilized, but is a very important part of these follow-up missions. So the first domes are currently there in Siding Springs. They're about to break ground to do the concrete platform. And so this was all budgeted or given by the SCFC PPRP award, which allows us to do this second step in Siding Springs. And so this design is actually meant to be on Sky for the 04 LIGO run. So we're planning on having this ready and on Sky in November. That's the plan. Everything should be on time for that, fingers crossed. So we'll have, again, the 16 telescopes on 2, so 32, and you can see it will survey the entire sky every 2 days. So you can see here, with 32 telescopes, we can roughly get about 2 days to paint the entire full sky. And so the full design for each telescope here, we can see we're about comparable with Assassin in field of view, about 80 square degrees. You can see the comparison to other facilities where we're comparable and where we can also match what other facilities are returning in terms of their data products. So now in the future, I also want to say that because of the philosophy of GoTo, it's fully adaptable and scalable. We can evolve in the future to match the needs of the gravitational wave community. So some examples of that would be if we want to increase the depth of our observations, we can co-point the telescopes to the same location and just get increased depth. We can do multiple search strategies. So one telescope is doing a large, searching large parts of the sky, and one is just sit on a specific spot. So while the current observing strategy is to observe the full sky every 2 days, we can adapt in the absence of a LIGO trigger to particularly in bright time. If we don't have a LIGO trigger, we can't make templates because we need dark templates. So what do we do with that time? It's possible that we could look into surveys. And so we can match the needs going on in the future for what the gravitational community needs. And so just an example of what has been done in the past, this was a pilot study run by Stuart Littlefair at University of Sheffield, where he proposed to use bright and gray time observations of the Milky Way. So what he did was he had GoTo look at the same patch of sky in 4-hour chunks, and then uncovered. So it's an unbiased survey sample of what is out there. And so you can see here, this is the typical pipeline output, because the way our pipeline is run, we take images, stack them, and make them deep. But because of the nature and the philosophy behind GoTo, we can actually adapt the pipeline to match the observable strategy. So instead, what we have here is we have a bespoke pipeline developed for just these searches where we can get really nice timing information. You can see the precision. This is about 19th magnitude in 60-second exposure. So you can see the precision of this white dwarf object that was picked up. Also, we also have some other objects that we weren't necessarily looking for. These are known objects, but these were picked up in the survey. This is a known cataclysmic binary. This is a known eclipsing binary, and these were just picked up in the go-to Marshall with the standard pipeline. So you can see the wealth of information that we can achieve without even looking for it. So these are picked up, and then we can take the data, which we have 1 minute time series, to then go in and look and do proper analysis with these types of sources. Okay, so I'll leave it with that. The summary, basically, we are wanting to contribute to the gravitational wave community. GoTo itself is adaptable. While we are currently right now very much in working towards 04 and having the proper template database and images for 04, so we can make that a success. It is, we are adaptable, and we can modify our search strategies in the absence of a line or trigger, and in particularly non-ideal observing cases to start looking for these verification binaries.
Thank you for the last talk. We take a couple of questions. Shane. So
Hi, yeah, that was great, Kendall. Thank you. It probably went by and I couldn't extract it from the slides.
We can't hear you.
You can't hear me? Hello?
I can, but I'm not in the room, so I think it's the Zoom that has a problem.
It's the Zoom room.
Maybe not just us.
I'll type it in the chat. Maybe they'll see it.
Still cannot hear you.
Yeah, so
I can hear
in
you.
the room we
Very well.
cannot hear you, but maybe
I'm talking now.
Yes, you
Okay.
are.
I'll type it in the chat.
we can hear you.
Now it's fine.
You can hear me now?
Yes.
Okay.
Yes.
So sorry. So Kendall, I was just trying to extract. I went by me on the slides. What's your magnitude depth and what's your time resolution if you sit on a source for data points that you can get off?
So in 60-second exposures, we can get down to about 19.8 in this wide.
Okay, perfect. Thank you.
Okay, we'll, in the interest of time, we'll move on to the next talk. But feel free to follow up after this.
Yeah,
So thanks again. So next up, we have a remote talk from Paolo Mocasio about stuff origin binary black holes with Lisa. So,
Hello, can you hear me?
Yes.
Good. Can you see also the slide?
Yes.
Perfect. Okay, so hello everyone. I'm Paolo Marcoccia. I am currently a PhD at University of Stavanger, and today I'm going to present you a work that I made with all the people listed over here. In particular, this work will lead to 2 papers that will come out very soon. And what I'm going to present you today will be the result mainly from the first one that focus on the SGBB, so stochastic gravitational wave background produced by stellar origin binary black hole in LISA. So I mentioned stellar origin binary black hole. I guess I don't have to spend much time on that because everyone here will know what they are. They are basically the main observed source of gravitational wave nowadays. So what we are considering are just 2 black holes that will meet each other, start spiraling, coalesce, and in this process will emit energy in the form of gravitational wave, like we can and generate on our detector some strain like the one that we can see on the right here from the figure that is taken by, I guess, the most famous paper about gravitational waves. As we also heard during this day, though, when we consider stellar origin binary black hole in the LISA detector, we know that we are not really, let's say, looking for a trigger for coalescence like in the case of LIGO. What will happen instead, due to the frequency range that the LISA detector has, is that what we will observe is the superposition of millions of events that are early spiraling. and most of them will not be resolvable. So what will happen is that in the same instant as the mission will start, all these events will start to superpose on the LISA detector and generate a strain that a confusion noise, we can define that is the stochastic gravitational wave background. So before spending some time properly defining this stochastic gravitational wave background, we have to, first of all, choose a way in order to predict the strain that will be generated by stellar origin black hole in the LISA detector. So how can we do that? It's pretty easy if we accept to pay the price. It's just to use the result that we got from the ground-based mission. In particular, we know that the LIGO-Virgo-Kagra collaboration over the last year obtained, let's say, several events from which they, generated several inference papers, and they described the population of black holes in our universe. So we can just use this result together with this formula to generate a population for our, let's say, for our observation. In particular, from this formula, we can see that on the left-hand side, we have the total number of binary black hole events at redshift zeta, and this will be given by a merging rate that is nothing more than, let's say, an estimate of how many binary black hole we will have at redshift zeta, given a certain amount of volume and time, times a volume, times a time, times a term that will hold all the properties of the event that we will generate. Indeed, we can just blindly use the result from LIGO because, as we mentioned before, the situation will be different. So let's start with the merging rate. We know that from the LIGO-Virgo inference paper, they propose both a constant merging rate and a redshift-dependent merging rate. The funny thing is that none of them will work in our case because actually the main limitation with LIGO is that nowadays they still observe up to 0 = 1. But in our case, actually, we will have to move further if we want to make prediction about the stochastic gravitational wave background. So what we decided to do is use the result of the paper that is listed below and use a theoretically matched star formation rate that will behave like the LIGO 1 up to 0 = 1, but then actually we'll have a peak and dampen off after, let's say, for higher redshift. Indeed, once the merging rate is defined, we just have to multiply that by a volume where we will choose the differential comoving volume of a sphere and by the total observed time T dot. I would also spend some time on this term because actually, let's say in principle, we can define it as the sum between the mission time, that will be the term that will take care of all the events that will drift in the detector frequency range during the time of mission, plus this term that is the maximum invent time of an event. This, the second term actually will instead take care of all the events that will be already ongoing at when the mission will start. So in particular, if we go to use this formula over here, where the tau is the residual time to coalescence, we can observe that indeed in the LIGO case, the first term, so the mission will dominate because we know also from data that actually events in the LIGO frequency range will stay for order of milliseconds. But in the case of LISA, the problem is that they will stay for several order of years. Indeed, I don't have to emphasize that will be unfeasible to simulate all the binary black hole in our universe for millions of years. But what we can use is that we know that events that are millions of years away from coalescence will have a really small amplitude in terms of strain. So we can just impose a cutoff on this point with max tau equals to 10,000 years for our simulation. So for now, we took care of the part that generates the number of events at redshift zeta. Indeed, as we said, this other term over here will hold all the information. In particular, what we are gonna define here are three different PDFs: one for the masses, one for the spin amplitudes, and one for the spin tilt. All the other parameters instead follow more or less an uniform distribution. Indeed, I wouldn't spend time defining this PDF because, I mean, they are well explained on the paper that is listed here. What I will say is just that we are going to use a power law plus peak model for the masses, where actually the only parameter that we change from the LIGO 1 is the maximum mass, that we set to 100 solar masses in order to have a more generical simulation. And by just plugging in the result, we will obtain something like this. The same we can do for the spin model, where we use the default spin model and obtain something like this. And for the spin tilt, again, we just use the default spin model. and obtain something like this. So we can finally move to the interesting part. To define the stochastic gravitational wave background, we know that from this paper, we already have an analytical form where actually by just assuming a model for the emission of gravitational wave during an spiral phase, in this case, actually, we are bringing, let's say, the most simple one without any post-Newtonian correction. We can generate analytically the stochastic gravitational wave background at frequency f, where actually this term are given by the 2 over here. What we are going to do is compare this method with a numerical generation of the stochastic gravitational wave background. So we will follow this approach. We assume a population that we already described before. We are going to compute the confusion background for this population. We assume a perfect subtraction of loud events, which means that if one event will have a SNR bigger than a threshold, it will be subtracted perfectly from the strain without actually, let's say, having to parameter estimate and stuff like that. And we can start to subtract all the events that will have bigger SNR irrespective to the both confusion noise plus instrument noise. After this part, we just have to loop the whole together, so they compute the background until we get to convergence. The good point of this method is that we are gonna both have the background and also the individual detectable sources with their SNR and properties. So if we go to compare the two, we can say that they agree. Indeed, before someone stops me, up to 2 main deviation. The first one is given by the fact that we choose a max-tau C cut, but as we can see, the main problem is that it's not something that we can feel by brute force. So the important thing is that we will obtain still convergence on the frequency range. And let's say actually observing that they converge, we can then use the analytical model in order to estimate the SGVB for future purpose. Furthermore, the second difference is on the fact that actually the analytical model generates the average of this SGVB without subtracting any source. But in our case, we will also have some sources that will be resolvable. What we are going to observe in particular is that the lower the SNR threshold is for, let's say, a source to be detectable, the more we will observe a bending on the rightmost part of the stochastic gravitational wave background, because it's the area where the most louder event will be. So if we just go to try to measure the SGVB level that was predicted by the LIGO posterior, we can observe indeed that, I mean, in most of cases, the measure will be quite good, and the uncertainties indeed will go down the more stronger is the amplitude of the stochastic gravitational wave background. We can give a brief look on the number of resolvable sources. Indeed, there will be another paper that will just emphasize on this and will explain the properties much better, but I'm not bringing that now. So what we can observe generally is that with an SNR threshold of 8, we are still going to obtain some resolvable sources, not too many, but I mean, it's still quite good because we can extend with the ground-based detector sources that we already have and have some sources at a different frequency range. But the main power of LISA will lie on the archival search. So for sources with SNR bigger than 4, that can be, let's say, cross-correlated with observation from other detectors and stuff. Lastly, I want just to give you a small look at another thing that we are working on before releasing the paper. And this, if a measure of the LISA stochastic gravitational wave background can improve the LIGO parameter estimation. What we've seen is that indeed it can, in the case where actually, for example, there is a correlation between the SGVB amplitude and 2 parameters in the parameter space. In this case, for example, we can observe that by going on the bottom right of this plot, the SGVB amplitude will increase. So getting a measure of the stochastic gravitational wave background indeed will cut down by a lot the area where it's possible to, let's say, the area where the parameters are acceptable. So I will just give you the conclusion. We've seen that by using LIGO Virgo collaboration result and some theoretical knowledge, we can simulate a population and the strain for the LISA detector. We can also predict the LISA foreground iteratively, and if we apply a SNR threshold bigger than 8 for the subtraction, we will observe that it will match with the analytical result, and we can hence use the analytical result under this assumption. We can also forecast the number of statistical properties of the LISA resolvable sources. Indeed, for now, I just shown you the number, but there will be another paper after the first one that will describe well also the properties of the statistical of the resolvable sources detected by LISA. We can also say that a measurement of the stochastic gravitational wave background with LISA will also help constraining parameters for the LIGO case. And indeed, the main point of this talk is that this method can indeed be easily updated with the future LIGO Virgo collaboration observation. And indeed, this means that actually before the LISA launch, we will already have a much better view of what we expect to obtain by the LISA mission itself. So thanks for the attention. I'm open for questions.
Thank you for the talk. There was a hand from Spicer, I saw too.
I can't hear well, sorry.
Tyson with the question.
Yeah, can you hear me all right?
Yeah, I can hear you well.
Okay, two quick questions. One, on this last bullet, you said it's easily adaptable for future observations. Did I see right that you're currently using the population from O2? And so if so, are you planning on incorporating the O3 results before finalizing this work?
No, actually, I'm using the O3 already, but the main thing is that the O3 updated, actually, that's why I kept the slide about the PDS. I mean, the main thing is that the O3 updated a lot the result on the mass distribution function, but actually didn't update at all, let's say, the result about the spin, because, I mean, actually, they couldn't improve that so much. So basically, we are tuned with the last O3 observation. Up indeed to the variation over here that we increase the maximum mass, but indeed, I mean, actually, even from the paper, you can deduce that it's still not set in stone the value of the maximum mass allowed. Then, I mean, indeed, the idea is that these parameters were set mainly for this simulation where we went to compare the analytical with the numerical model. But then actually you will see from the paper that we also, for example, to produce this plot over here with the numerical sources, let me see. I mean, also this one and this one. What we did was running through all the LIGO posterior of O3. So, I mean, the main idea is that that parameters were used to compare, but then actually the proper analysis was made with the whole posterior from the LIGO 3, where actually all the parameters will change.
Okay, great. And then what's the LISA observing time you're assuming to get these number of detectable events?
4 years at the moment. 4 years, 100% efficiency.
All right, thank you.
Okay, thanks. We'll move into the next talk. So one more round of applause. Next up, we have Kevin Burge, characterization of detectable binaries using optical and time domain surveys.
All right. So let me share. Can you guys see this?
Yes.
Okay. So thanks for letting me give this talk. And I don't have a lot of time and I have way too much to talk about. So this is going to be rushed. But feel free to talk to me afterwards. I can talk people's ears off about these things for like 10 hours straight. So what I'm going to be talking about are progress and prospects in detecting milliards binaries using electromagnetic waves across the entire spectrum. And so I'm going to rush through the introduction and just say briefly that there are lots of different types of things we can detect with gravitational waves. And this talk is going to be focusing exclusively on the resolvable and unresolvable galactic binaries. One plot I like to show in all of my talks is why LISA is such a natural tool for studying white dwarfs. So something I want you to pay attention to is the peak frequency of LISA is about 10 to the minus 2 hertz. If you look at the equation of state of fully degenerate, electron degenerate matter, what you get is a mass radius relation, which you see on the top. And what that lets you do is you can also write a density mass relation, which you see on the bottom. And that's a particularly useful way of sort of thinking about a binary, because there's this remarkable property that the orbital period at which an object overflows its Roche loop in units of days is approximately equal to 0.43 divided by the square root of the density of that object in grams per centimeter cubed. And this remarkable relation is very insensitive to what the accretor mass is. This works for mass ratios up to about 100. And what that means is I can take this plot of density versus mass and quickly give you an orbital period characteristic of degenerate matter interacting with the companion and overflowing its Roche lobe. And degenerate matter, basically electron degenerate matter from this equation of state is describing the maximum density that matter can reach in a sort of an optimal configuration. What you're seeing is, of course, the orbital periods for which most white dwarfs will interact with their companions are between 10 to the 1 and 10 to the 3 seconds. You can take 2 divided by that and go right back to the characteristic frequencies that Lisa's sensitive to. So it's really the perfect machine for probing compact objects like white dwarfs interacting with another compact object. Okay, just some quick background. Now I'm going to jump into the actual survey bit of this. So most of my work so far has been done on the Zwicky Transient Facility survey based at Palomar on the 48-inch Samuel Ocean Schmidt telescope. I'm also now starting to use TESS and have successfully recovered quite a few interesting systems with that at this point. And I'm gearing up for the Vera Rubin Observatory, and I'll talk a little bit more about that. But just to say, ZTF was a particularly nice survey because compared to all other surveys that reach comparable or deeper depth because they have bigger apertures, and you can see sort of the footprints of those on the right, ZTF just has a huge field of view. And what that lets ZTF do is accumulate a lot of images very quickly. And with LISA sources, that's kind of important because if you wait around too long, they don't have coherent waveforms because they have substantial F dots. And so if you wait too long, you're gonna have to do acceleration searches, which is computationally expensive. And believe it or not, computing is a pretty big issue here. I always show this slide. I just say, if you want to do massive searches of electromagnetic data for millihertz binaries, you need tools like GPUs to solve the problem. GPUs are essentially extremely powerful pieces of computer hardware optimized for doing things like matrix multiplication operations. And it just so happens a lot of the search algorithms that we have and that I'm developing are essentially boiled down to matrix multiplication operations. And so I've built a lot of hardware myself kind of optimized to do this. And something I can brag about is this box you see here on the right that I assembled. It's the box where a lot of the results you're seeing today came from. I was not using a cluster, I was using a desktop in my office. So just a couple of quick updates on the algorithm side before I jump into actual results is, well, I just told you period finding is much faster on GPUs than on a CPU when it's implemented correctly. And leveraging that speed, I've now also successfully implemented a fast coherent acceleration search based on a GPU, optimized for large-scale time domain surveys operating on a fixed field grid. Just a quick aside, the reason the fixed field grid is important is you can then batch objects that share the exact same timestamps, which as long as your field of view isn't too large and the BJD correction is small, is totally fine. And then one of the bottleneck steps in many of these algorithms, which are computing trig functions, for example, you only have to do once for many, many objects, and you basically cut the runtime significantly by exploiting this trick. Those acceleration searches are going to be really important in the Vera Rubin Observatory era. And I am completely confident that if I had 10 years of LSST data today, and I had the LISA source catalog, that I could basically go in and pull out F dots for a very large number of sources within a couple days. I have the infrastructure ready to do that already. And so what I've done with this infrastructure, because we don't have those data sets yet, is I've now exhaustively period searched 1.22 billion sources in ZTF data up to frequencies of 720 cycles per day. This is an unbiased search, just every source of light that had 5 pan-stars detections or more in the ZTF footprint I searched with forced PSF photometry. There is a lot there, and I'm going to be showing you some of the new things that have come from this. But before we go to the new stuff, let me just briefly mention a little bit of the old stuff. Many of you probably already know it. sort of out of the original run of looking for these things in ZTF with the older photometry and more targeted selections, there were already 15 ultra-compact binaries. Many of these are pretty low signal to noise in LISA, but a few on the short period end are substantially loud LISA sources like J1539, which I'll talk a little bit more about. And the modulation of the electromagnetic flux arises primarily from two phenomena. Eclipses, like you see in the little toy movie on the left of the 7-minute binary, but also ellipsoidal variations, where basically you're seeing the tidal deformation of one object orbiting another compact object. Those are pretty important because you can also find the neutron star and black hole systems that way. And so I just like showing this movie. We've been doing lots of follow-up still on those systems as well. This is a hypercam light curve of ZTF J1539. On the left, you can see the actual image. If you look in the lower left-hand quadrant, you can watch a star disappear every time there's the eclipse. That's the 7-minute binary. And I just briefly want to talk about this one to illustrate how valuable the electromagnetic observations are. And this is something I'm going to come back to again and again. Let's talk about how much you can learn from a light curve just by looking at it. So we're looking at a light curve, and one thing you can already see about this binary is there's this huge out-of-eclipse quasi-sinusoidal modulation. That tells you one object is heavily irradiated by the other. Not something you're going to see with gravitational waves. You see a couple of eclipses, in particular remarkably deep primary eclipse. And I just want to show you how much I can read off about the properties of these systems without even doing anything quantitative. One is, I know the inclination's close to edge on. There's an eclipse. That's pretty straightforward. And when I model this light curve, of course, quantitatively, I can measure it to better than 1/10 of a degree. I immediately know that the temperature of object 1, the one being occulted during that primary eclipse, is much, much greater than object 2, because basically the depth of that eclipse is telling us something about the surface brightness ratios of the two objects. Again, something you're never going to get from gravitational wave data. That's not going to tell you about the temperatures of the components. I can also immediately infer that R1, basically that hot object, has a smaller radius than the secondary. And that's because the hot object is fully occulted during the primary eclipse. And so the cool thing has to be big enough to completely block it. And then I know these are degenerate matter. And so I also know from the white dwarf equation of state that, well, smaller white dwarfs, especially smaller, hotter white dwarfs, are going to be more massive than cooler, more bloated companions. And of course, when I model these quantities, I can do better than just write down inequalities. I can make pretty precise predictions. But I just want to show you just how information-rich an electromagnetic signal is. You've basically got a complete picture of the system just with a cursory glance at the light curve and not even modeling it. As I say, there's lots of other cool stuff that comes with multi-wavelength observations. Here's some HST data on that same source. You see the irradiation basically completely vanishes when you go to the ultraviolet. But the primary eclipse is there as expected. Okay, so I want to also move on to new results. So I'm just going to keep powering through this. But I just want to say part of the program has been timing these sources. This is an out-of-date plot from my thesis defense last year. We've more than doubled the number of sources for which we have P dots now, and that number is continuing to increase rapidly. By the way, these P dots can get pretty precise, and I've done calculations for the longer period sources, like 40, 50 minutes that LISA detects. We'll be able to pull out the P dots much more easily using electromagnetic data than one will be able to with gravitational wave data. So it also gives access to chirp masses for systems at lower frequencies that LISA doesn't have the frequency resolution to see the evolution of. And so I'm going to keep rushing and just say these red points were sort of the points that had been added at the time of my thesis by ZTF in terms of verification binaries. As I mentioned, not all are above the sensitivity curve or particularly high signal to noise. There is a pretty heavy bias towards systems that are edge-on, which you see circled in blue. But I'm continuing to rush because I really want to get to exciting new results. And just say I've added a lot in this place. This plot is out of date, and there are many more of them at this point. So just a brief preface to some of the new systems is, what are we learning from these? Because I've heard this comment of, oh, do we really need new verification binaries? I don't care whether these are verification binaries. These things are amazing. Even if we didn't have a LISA signal coming in 10 years, I can still write amazing papers about these things because of the types of evolutionary channels we're probing, for example. And you're going to see a couple of examples of those. There's a huge diversity of them, and in a lot of cases, we're finding prototype systems of really the first examples of some of these channels ever observed. We're probing things like tides and white dwarfs. We can do that with CTFJ 1539 just based on timing and measuring F double dot in the optical. We're getting some of the most precise parameter estimates for white dwarfs out there, believe it or not. I like to brag that the 7-minute binary is one of the most distant white dwarfs known, yet it has one of the most precisely measured radii of any white dwarf. That's one of the nice things that happens when you stick these things in close binaries. And the thing I want to emphasize is this is all science we can do with photons. The gravitational waves are kind of just going to be the icing on the cake, in my opinion. And I know this is a 15-minute talk, so now I'm going to rush to actually show you some of the new exciting things coming out of all of this work. So first, something already published. So this came out of a search for ultra-compact systems. It's not LISA detectable. I found something that looks like it could be a Black Widow pulsar in an hour orbit. Which is starting to get into interesting frequency territory for LISA. Unfortunately, this particular source, the chirp mass is so low and it's distant enough that I think it's hopeless to detect. But there could be something more nearby because these things are very faint. So I wouldn't be surprised if there's one sitting at 300 parsecs or something. You can read the paper about this. It came out about a month ago in Nature. The one I want to talk a little bit more about, which I just submitted the second round of referee reports for, is this system. So it has a 51-minute period. You can see the light curve there on the right. And one of the first things that'll probably jump out is it has a primary and a secondary eclipse. And that's really, really nice because they're total eclipses. And I'm going to tell you why it's nice in a moment. But the period's 51 minutes, and so when I first saw this light curve, I guessed, oh, this is probably some bloated ELM white dwarf filling its Roche lobe accreting onto a CO white dwarf. Then I went and took a spectrum and was absolutely stunned. This looks like an F-type star. This is not what a white dwarf spectrum looks like. And you can see the beautiful trail there on the bottom of just all of these lines Doppler shifting back and forth. For those of you who like AMCVNs, or as I like to call them, helium CVs, this should excite you. This is basically that progenitor channel, which often gets kind of disregarded in favor of helium stars and double white dwarfs. This is that evolved CV progenitor channel, or as I like to call them, transitional CVs, because what effectively is going to happen is this is going to switch from hydrogen to helium accretion. The system is accreting. That spectrum is co-added in the rest frame of the donor. If you look in the rest frame of the accretor, there's a nice accretion disk with double peaked emission, both hydrogen and helium. And so the nice thing is because the system is Roche filling, has a primary and secondary eclipse that are total, I can actually completely solve the system with exquisite precision. I know these masses to a couple %. It's actually one of the best characterized of all CVs known, funnily enough. And what those parameters let us do is actually make very constrained MESA models, because we can input what both masses are, both radii, and so on both temperatures. And this will evolve nicely into the LISA band. So we predict a period minimum of about 18 minutes. And so the takeaway of this source is, one, it shows this evolved CV, or as I like to call them, transitional CV progenitor channel for ultra-compact systems is definitely viable. And not only does it reproduce the systems in the longer period end, but critically, it's also going to reproduce the short period systems, which I think some people had doubted in previous literature. Some of the systems we see in the LISA band definitely will be coming from this channel, and it actually may be a large fraction because this source is surprisingly bright and nearby. Okay, next system. So by the way, this one will be hopefully published soon, so you'll be able to read lots more about it. And there's actually already a preprint on the internet, just not on Archive. It's on Nature's preprint server. But I can send a link to it if you contact me. Okay, next system, which I'm currently working on writing up, 13.7-minute orbital period. This one's comfortably in the LISA band, accreting. The brief thing that I just want to mention is, all of these accreting LISA sources, typically we don't see the donors. This one's amazing because the donor is warm. you can actually see it. It's like 20 to 30,000 Kelvin. Probably came from either an SDV progenitor or an ELM white dwarf. But it's actively mass transferring. It's got a disk. You can see it in the spectrum. The disk actually transits the donor. So it shows basically these things that we had known exist, ultra compacts with visible hot donors from the SDV channel. They're also in the LISA band. At least some of the sources we see with LISA will absolutely have donors that we can measure radial velocities for. And these velocities, of course, are huge, as you can see here. And like I say, the system is nicely detectable in LISA, has an X-ray counterpart, has orbital decay, so it's still on the way in, so on. I don't have enough time to talk more about it. There's also a sub 8-minute AMCVN, which I don't have time to talk about. I'll just mention it exists, and I'm also working on writing it up. And looking to the future, I'm out of time, so I'm just going to say things are going to get a lot better. LSST is going to be a game changer. Roman, I think, is going to be a game changer. A lot of the X-ray missions that are currently developed are going to be game changers. And on that note, I'm going to end with a slide to say I'm actually involved with one of these X-ray missions, and I'm the only ELISA person currently involved. It's called Axis. It has enough of a field of view that it could actually tile the entire sky with a survey if it wanted to, and do an eRosita depth survey in 1/10 of the time. That's not how it's planned on being used. It's more of a geo instrument, but I'm making a big pitch that we need to basically hammer the galactic plane with this thing to get archival X-ray data, which we will then cross-match to LISA to find ultra-compact X-ray systems. And I'm going to wrap up there because I know this is only a 15-minute talk. Sorry for going a bit over.
Thank you for the great talk. We don't really have time for questions, so I think we'll just move on to the next one. But feel free to send me an email, message me on the chat. I'm happy to talk more if anyone wants to. So next up is another remote talk from Jordi Davler, probing black hole shadows via electromagnetic self-interacting sublenting.
Hi everyone. Let me get rid of the Zoom. Hi, so you should be able to see my first title slide by now. Thanks for the invitation to be at this great meeting so far. So my name is Jordi Davler. I'm a postdoctoral fellow at Columbia University, and I work together with Professor Zoltan Heyman. And the title of today's talk is about looking at black hole shadows in black hole binaries by looking at their self-lensing features. So why are self-lensing flares interesting? Well, during the last couple of days, many people already pointed out that AGN variability can be hard to distinguish with respect to an actual binary variability. So like we have 150 candidates so far found with large time domain surveys where they look for Doppler modulated signatures. But as people pointed out, like the red noise variability of an actual AGN can actually very well mimic this Doppler modulated signals, especially if you only have like 1 or 2 periods of light curve data. So one way to go around this is to be more lucky in the way that you need to observe black holes closer to Adjon. But if that actually happens, quite interesting things start to happen, namely relativity happens. So one very peculiar candidate in this set of 150 candidates is called Spiky, which was already observed by Kepler in 2010. And the light curve of these observations I show here on the right. So on the y-axis is the magnetification as a function of time, and the black dots indicate the Kepler data. So there are 2 intriguing effects happening here. First of all, you have the sawtooth pattern, which you would expect to arise if there is a binary in an eccentric orbit. In this case, you don't get the typical sinusoidal pattern that we often see, but due to the skewness of the light curve comes by, the velocities start to vary along the phase of the orbit. And additionally, of course, there is this large feature here in the center, which is why it's called spiky. There's a massive spike, a massive flare, which happens to happen exactly at the moment where you expect the two black holes to align, namely when you go from a deboosting to a boosting scenario. So the velocity component of the black holes is perfectly in plane and starts to change sign. So yeah, you have like a eclipsing black hole binary. So what happens then? You have a black hole in the foreground, a black hole in the background. The black hole in the foreground, of course, curves space-time and starts to act as a gravitational lens, which starts to alter the amount of emission that you observe. So it starts to curve the light towards the observer, and more of the emission of the black background source starts to be observed by our telescopes. So Hu et al. Also compared a simple microlensing model to the actual data, which is shown here in blue and in green, which shows a remarkable fit for a black hole of 10 to the 8 solar mass, eccentricity of 0.5 and a mass ratio of 0.2. I think the inclination was around 80 degrees, where 90 means perfectly agile. So it's like 10 degrees of the orbital axis, but it shows a remarkable fit. However, microlensing is only like an approximation, really, because in that way you assume that the deflection angles are small and that the distance between the actual lens and the source are typically very large. So if we want to study these self-lensing in a more general fashion, especially to see if they're interesting also for more compact binaries, we need to do something else. And that's what we did in the two papers that we had published in PRL and PRD this year. So what we set for ourselves as a goal is to actually study these self-lensing flares with general relativistic ray tracing. So for those not entirely familiar with general relativistic ray tracing, it's a method where you have a virtual camera somewhere positioned outside of your domain of interest, which can be like a GRMHD simulation or just some semi-analytical prescription of your accretion flow. And then this camera consists out of multiple pixels. Every pixel is assigned a wave vector, and this wave vector is integrated with the geodesic equation to compute the trajectories of the light in the curved spacetime. Along these trajectories, we can then solve the radiation transport equation to get a feeling about how much emission is actually measured at every one of these pixels on our camera. Well, we do this with the GR ray tracing called Raptor, which is also used for Event Horizon Telescope analysis. And the model that we included is a semi-analytical model. We just try to do something simple so we could actually do some kind of a parameter survey. So what we did is we have like two black holes on a Keplerian orbit or going around each other. Both black holes can be spinning or non-spinning. The Keplerian orbit can be eccentric or non-eccentric. We can alter the inclination, the masses of the black holes, the mass ratio between them. And in total, we come up to like roughly like 27 models in total. Well, given that, of course, this is like what, like a 12-minute talk, so I of course can't go over all 27 of them, but I will try to highlight the most important result that we think, personally, I think it's the most exciting result that we found. I would like to highlight that in the remainder of this talk. But feel free to ask me anything about like other dependencies. So first of all, to get a little bit familiar on how these systems work, I really like this nice visualization by Jeremy Sneedman. So there's like this accreting black hole with like a beautiful thin disk in the equatorial plane. You see that the material is moving around, and you get like this lensing effect on the above and below the plane because of the bending of the light. And there are a couple of interesting features in there that you will also start seeing in my models. So the lensing, of course, on the other side, there's the Doppler boosting or deboosting on the other side. So the material moving towards us is brighter than the material moving away. And additionally, there's also a photon ring. The photon ring, you will not see it that much in my models because we actually extended the accretion disk from the ISCO all the way to the event horizon, while Jeremy puts the accretion only up to the ISCO itself. And in the center, there is, of course, the black hole shadow, which is like the thing that the EHT measures. So it's like a flux depression in the center of the image that coincides with the putative position of the actual black hole's event horizon, only then a little bit more enlarged because of the gravitational self-lensing of the actual black hole itself. So this is a self-lensing model where we view the orbital system or the system from like 87 degrees, so almost perfectly edge on. There's a binary separation of 100 gravitational radii. It's a 10 to the 7 solar mass black hole binary. It has equal masses, and it is observed in this case in the X-ray. So we just assume some thermal emission that is produced by these accretion disks. And as you can see, as these black holes move and as they move in front and behind each other, like the background black hole is like curved around the Einstein ring and starts to create like these lensing patterns, which we expect that imprints also a signal in the actual light curves. So if we then start looking at the light curves for a 90-degree case, so this is a perfectly edge-on case, the light curve is shown here at the bottom. So this is like some flux normalized to some arbitrary value as a function of phase, which is just like the time of the orbit divided by the orbital time. And as we go to like a quarter or 3/4 of the orbit, we see indeed these clear indications of a self-lensing flare, relatively similar to what we saw in the spiky case. However, in the center of these self-lensing flares, there's actually some dipping feature that confused us by quite a bit initially, because this was not mentioned in the literature before. But there's actually quite an elegant physical reason why we would expect such a dipping feature to be present. Most works actually just looked at point source models, so there's not really an emission morphology that was included in their modeling. Well, we actually have like these ring-shaped images, right? So if you have the focal point of your lens move over a ring-shaped image, you would expect that when the focal point is on the left side of the ring, there's a lot of emission that it can amplify. In the center, there's almost no emission, so you would expect the self-lensing flare to go down. Well, on the right side, there is emission again, and it goes up again. So this kind of gives like a dipping feature within the actual flare itself. So this is interesting, of course, because if this feature also nicely correlates with the actual black hole shadow size, we can not only use it to like show that there are actual horizons in these black hole binaries, but also maybe say something about the sizes of their shadows, which are actually tightly constrained by general relativity itself. So if we then measure the width of these dips and compare that with the expected time it would take the lens to move over the black hole's apparent size, we find that it exactly matches, especially for the optically thin case where you have like a beautiful sharp boundary, which coincides with the photon ring. There's a perfect one-on-one agreement of like 10.4 gravitational radii, which is in the literature the black hole shadow size. So in that way, like this method, if we could actually observe this by using like optical searches, this is an intriguing way to actually find black hole shadows that are unresolvable by current VLBI arrays, such as the EHT, because we are not limited by spatial resolution, but more by time resolution. Well, I already hear you thinking like, well, that's great. You're looking at like an inclination of 90 degrees. What happens if we're not that lucky? Well, things become a little bit harder as when you move away from the perfectly edge-on case, of course. So for the 100 gravitational radii case, I show here like multiple light curves at multiple inclinations. And if you go from 90, which is the red line again, to like 87, might be hard to see this yellow line. The dip starts to disappear because at that point your lens doesn't move anymore over your black hole shadow feature. So there is like a 3-degree window for 100 gravitational radii binary. So it's not that bad, but still you need to be lucky. So we actually need kind of the big numbers. So let me see, how am I doing on time? Let me skip to the actual search strategies. So how to find this dip? So if we look at the current data, the current candidates, like this distribution of masses is more skewed towards like the high mass regime. So this is sadly outside of the LISA band with like 10 to the 9 solar masses. but they're like typically a year. And if we then make like an estimate, so the dip that we see for these sources should like be visible for a couple of days, and the inclination window is a couple of degrees at most. So if we then assume that the orbital inclinations on the sky are uniformly distributed between 0 and 90, like you have like roughly a 1% probability of finding the dip in the current data. Well, this is of course a very naive estimate, because on the other hand, these sources were observed via Doppler boosting. So they are already skewed more towards edge-on systems than face-on systems. But on the other hand, we did not take into account for this estimate also for mass ratios other than unity, and that would also complicate things a little bit more. But anyway, like roughly like a 1% estimate. So we have currently like 150 sources. So a search strategy is at least to like look at the current candidates that there are, and look especially also at spiky to see if there is substructure within the self-lensing flare itself. And as we already heard before, like Vera Rubin's Observatory's LSST is of course going to give like a whole gold mine of like AGN sources. We're going to like track 100 million AGN targets. So there might already be a lot of interesting sources in there as well. And additionally, of course, with LISA, when we are in the pre-merger phase, and we can use these self-lensing flares to help look for like localization, sky localization, and maybe even get some information about the shadow size as well. And what makes it interesting also is because of the orbital period measurement that we can do based on like the Doppler modulation, it already tells us what the mass of the black hole is. If we know what the mass is, we know how large the shadow should be. And if we know how large the shadow should be and we compare that with what we measure, we can actually maybe also say something about GR in that sense. Yeah, I think I'm not sure how much time do I have left?
You've got about 1 minute left.
1 minute left. Okay, that's great. So let me give a very preliminary outlook. These are, of course, models that do not include any time variability, because they're just like these semi-analytical constant flux slabs that just radiate around the black hole. So there is no temporal variation as you would expect from a simulation. So we're actually started working on that now as well to see, okay, if we use a hydro simulation of a circumbinary disk where there are two black holes orbiting around each other, what kind of spectral shapes do we get? What kind of velocity profiles does it give us? It also gives us the circumbinary disk, which might partially actually block the view to the inner black hole, right? Inner black hole binary, right? And there's of course the accretion variability that will start to compete with the actual self-lensing flares. So for that, I'm working now with a graduate student at Columbia, Luke Krauf, who coupled my ray tracing code Raptor to the GPU hydro code Sailfish, and I can like show like a very first preliminary image of that. So this is an actually ray traced hydro simulation where you can see that the foreground is actually blocked by the circumbinary, and there is some circumbinary material lensed in the back. You can beautifully see this like mini disk being lensed around the foreground black hole, and there are these streams here in the center that get lensed as well. So that's all very exciting, and I'm very curious to see what kind of light curve will come out of simulations like that. And I'm very excited about the future, and I'm happy to talk more and answer any of your questions or talk more offline on this. I will leave my summary slide up. Thank you very much.
We can take a question if there's any online, obviously. If not, we can move on to the penultimate talk. Thank you again. So,
It hold one hand, just one up. From Alexei.
Yeah, sure. Alexei?
Yeah, thank you. These are beautiful visualizations and simulations. And I was wondering, just following the thought of simulating ray tracing in further context. So if you have a binary black hole which is merging and producing gravitational waves, and there's a triple companion next to the binary black hole, so can one do something like ray tracing simulation to see how the triple companion will affect gravitational radiation signal from merging binary? Because, I mean, gravitational radiation also follows geometric optics in some limit.
Well, that's a little bit out of the scope of my expertise, I must admit, but I can imagine that there is some lensing then of the gravitational waves as well, right? Because I think that that is what you're like pointing towards. So if you have these binaries orbiting, then you would get gravitational self-lensing as well, which would amplify and put an imprint on the actual waveform. So I could imagine, yes, but yeah, that is, I must admit, outside of my expertise.
Okay, thank you. Interesting.
Okay, let's thank Julie once more. So next we have a remote talk, Srija Chakraborty, probing SMBH progenitors by redshift with Lisa.
Hi everyone, I hope you can see my screen and hear me well too. I'm Srija and I'm working with Simona Gallerani at Scola Normale Superiore, and I'm going to talk about probing supermassive black hole progenitors, high redshift with LISA. So a quasar, as most of you know, is an extremely luminous active galactic nucleus in which a supermassive black hole is surrounded by a gaseous disk. Discovery of over 200 quasars with masses reaching up to 10 to the power 10 times solar masses have been made possible by various surveys at redshifts as far as 7.64. For several of these sources, it has been possible to determine the mass of the black hole thanks to the detection of the MG2 line arising from the Aegean innermost region. It is found that the supermassive black hole mass can reach up to 1.1 times 10 to the power 10 solar masses, and it's very interesting to ponder how such massive structures formed in less than 1 giga-year. Many models exist to provide a theoretical background for the existence of such massive black holes at such high redshifts. And for this, it is important to detect and study the properties of the progenitors of the supermassive black holes. So one of the most promising upcoming instruments to probe such supermassive black hole progenitors is LISA. Otherwise, I wouldn't have been spoken here. So as you know, LISA is designed to launch at 2034. And with an Earth-like heliocentric orbit, it is expected to detect galactic compact binaries, EMRIs, massive black hole binaries, etc. For sources entering LISA, we can infer their initial distance of separation, time to coalesce and observe, characteristic strains, and so on. There are several other parameters associated with massive black holes, but for our work, we only consider black holes with zero spin. So we are interested in high redshift. So by that, I mean between redshift 6 to 12 massive black holes with seed mass between 10 to the power 5 and 10 to the power 7 solar masses. We observe the typical life cycle of such a binary, which consists of the inspiral, merger, and the ring down phases, where in the first stage of the inspiral, it basically consists of gradually shrinking orbits of the binary. It goes on for a very long time. Gravitational waves are very weak as black holes are quite distant to each other. As the black hole orbit shrinks, the radial speed increases and the gravitational wave gets stronger. Innermost stable circular orbit is the last stage of orbit before transiting from inspiral to merger, where in the merger phase, the gravitational wave peaks to finally transition to ring down, where after the merger, the single black hole settles down. It's possible to detect the merging massive black hole binaries through LISA, and hence it is perfectly suitable to look for the supermassive black hole progenitors. So we use zoom-in cosmological simulations, Gadget 3, to track simulated massive black holes growth by merging through and accretion. A flat cosmology is assumed in agreement with results from the Planck collaboration. First, dark matter only low resolution simulation is carried out in a box size, which is different for different resolutions. The cosmological box is then evolved from redshift 100 to redshift 6 using periodic boundary conditions. The most massive halo is then chosen at redshift 6 and resimulated with a higher resolution or zoomed in. So we analyzed two sets of simulations, V21 based on the works of Valentini et al. And V18 based on the works of Paray et al. These simulations mostly differ in terms of AG and feedback models and resolutions. So at redshift 6 in the zoomed in region, the highest resolution particles have a dark matter mass of 1.5 times 10 to the power 6 solar masses for the B21 case and 7.54 times 10 to the power 6 solar masses for B18 case calculated over the smoothing length. So basically, it's almost higher by 3.5 times in the B18 case as compared to B21. In the figure, you can see the spatial projection of the gas density in the two different resolutions at redshift 6. The black circle in the Barai image is the view radius of the most massive galaxy at redshift 6. We see that the central black hole is embedded in a complex large-scale structure. The central regions are gas-rich, feeding the central black hole as the structure grows. In our models, a black hole of 10 to the power 5 solar masses is seated in a host galaxy wherever the halo mass exceeds 10 to the power 9 solar mass, if it doesn't already have a central black hole. These black holes mimics the direct collapse black hole scenario, where the idea is that the seeds of massive black holes are formed due to collapse of primordial gas, which contracts without fragmentation. And this is the model we use for our theoretical consideration, and these black holes then grow by merging and accretion. We have considered two cases of AGN feedback for each set of resolution, whereby AGN feedback, if I explain very briefly, it's basically black holes grow by accretion as well as by merging. A fraction of the accreted rest mass energy is radiated away, a fraction of which is further coupled to the surrounding gas of the black hole as feedback energy. So for the kinetic feedback models, in the B18 case, energy-driven winds drive surrounding gas outwards in either a spherical geometry with 90 degrees half opening angle, which we call the AGN sphere model, or a biconical geometry with the black hole at the apex, which we call the AGN cone model. And for the thermal runs, AGN feedback is coupled thermally and isotropically with the surrounding gas, and a control run with no AGN feedback involved is considered. So here you can see the merger rates predicted by each AGN feedback scenario plotted with respect to redshift for the chirp mass range less than 10 to the power 6 solar masses, where our AGN feedback models will be comparable to the Hartwig et al. And Cezanne et al. Models of similar redshifts. And so the CBHs, we have chosen Warner blocks of 30 times 10 to the power minus 21 and setting the efficiency parameter at 1, which subsumes all the internal parameters of the direct collapse black hole formation. This model of Hartwig et al. Can be directly compared to the models of Cezanne for similar mass seeds with mergers occurring due to mergers of host galaxies, and the two models are based on semi-numerical calculations by Begelman, but two cases are considered. So the first BRHF, where the star formation rate exerts high level of stellar feedback and ensures a rapid metal enrichment. So the DCBH formation stops earlier, so around redshift 18. And the low feedback model, where the stellar feedback is milder and halos remain metal free longer. So the DCBH formation stops around redshift 15. So in case it's not very clear, the labels, the blue line stands for the AGN cone case, the red stands for the AGN sphere case. The dark green line is the fiducial case, which is the thermal AGN feedback case of Antony, and has been chosen as our fiducial case due to better resolution. The merger rate falling strictly between the high and the low stellar feedback from Cezanne's work and is compatible with the optimal line Warner flux from Hartwig et al.'s work. You can also observe the merger rate trends for all the models for chirp mass range between 10 to the power 6 to 10 to the power 7 solar masses and greater than 10 to the power 7 solar masses. More number of mergers observed in the kinetic due to heavier mass distribution of black holes. And takeaway message is that the merger rate depends on the resolution of simulation as well as the feedback implemented. Within the framework of our simulations, the initial distance of separation from merging black holes is in the kiloparsec scales. However, the LISA regime, as you know, is in the order of milliparsecs. So we calculate the initial distance of separation from the LISA frequency for binaries of given mass at a given luminosity distance. We show here the evolution of the initial distance of separation of the merging massive black hole binaries with redshift and Chirp mass of the system. The filled circles represent the events which are detectable by LISA, and the unfilled are undetectable. So basically, the threshold for detectability is set at the signal-to-noise ratio corresponding to 5, and the edge colors are representing the Chirp mass range of the events. We find that low-mass systems start out from a high distance of separation in the LISA band at the same redshift for all resolutions and feedback, and more massive systems merge outside to the LISA band owing to its small distance of separation to begin with, once it enters the LISA band. Similarly, we show the variation of coalescence time, which is basically the time it takes for the binary to merge from when it enters LISA band, shown in days, with respect to redshift and Chirp mass. The coalescence times in thermal feedback models are less by almost a factor of 2, with the mean value of the kinetic feedback models to be at 55 days, which is more than twice the values of thermal resolution, so 25 days. So given a steady detection rate of LISA, different models can be distinguished comparing the extreme values of However, it's more interesting to look at the actual available time to observe the massive black hole binaries with LISA. Once we set the threshold of detectability for LISA, which we assume to be at an SNR corresponding to 5, we calculate the available time to observe the massive black hole binaries with LISA from the time they have accumulated enough SNR to be detectable. This parameter is important as it gives us an estimate about the actual time that will be accessible for following up a LISA detectable event with contemporary electromagnetic instruments. In general, we find for the V21 simulation runs, the available time to observe range between 4 days till almost a month. For B18, we find the available time to observe to range between a week and around 2 months. So for both cases, we have optimistic time spans to be followed up by different electromagnetic instruments. So an inspiring binary is detected if the SNR integrated over observation is greater than the signal-to-noise ratio assumed for detection. Here, as I already said, we assume the threshold for detection at signal-to-noise ratio corresponding to 5. And we find that the further sources, so we expect the further sources, the lower should be the SNR, but we also see a higher SNR for sources with low Chirp masses. This is because low mass binaries merge slower, so stays in LISA bands for longer and accumulates more signal-to-noise ratio over its lifetime. To give a qualitative idea, here you can see the coalescence mass distribution with respect to the mass ratios of the massive black hole binaries in 4 feedback models, where the white space in the bottom right represents the non-analyzed binaries due to our resolution limits, and on top left, the white bins correspond to the binaries falling outside the detection window. In all cases, we see that the maximum number of events occur for equimassed binaries for low masses. So just seated binaries have a higher probability of merging as compared to black holes which grow to higher masses through merging and accretion. So we also calculate the angular resolution of the detectable merger events of our fiducial case from the signal-to-noise ratio for the possibility of complementary electromagnetic detection of the gravitational wave events, and track the redshift evolution of the angular resolution for different mass ranges of the merger events. We find that we have better prospects of localizing our detectable gravitational wave events for low mass binaries at lower redshifts. And this localization is important for other electromagnetic facilities to follow up the gravitational wave events, which brings us to the possibility of detection of gravitational wave events through electromagnetic counterparts post-merger. We use a distance threshold at each redshift pin for the coalescing binaries to associate them with a host galaxy and calculate the UV luminosity, the X-ray luminosity, C+, and the far-infrared luminosities for the host galaxy to further probe the galactic properties hosting a LISA event. Sorry? Yeah. From all the events in our fiducial model, we select cases which are bright in different electromagnetic bands, by which I mean a UV magnitude of at least -21, a far-infrared luminosity greater than 10 to the power 12 times solar luminosity, and X-ray and C+ luminosity of at least 10 to the power 8 solar luminosity, and also with a detectable signal-to-noise ratio in LISA. So the UV luminosity is taken as the sum of the UV flux due to the star formation and aging. And we find in our fiducial model, out of a total 56 events associated with host galaxies, 33 events are bright in UV band, with a further 32 events being detectable by LISA. We calculate the X-ray as the integrated luminosity in the 2 to 10 kilo electron volt range, and we find for our fiducial model associated with host galaxies, for every 40 LISA detectable events, around 19 are detectable in the X-ray band out of a total 35 X-ray bright events. The C+ luminosity originates from the photodissociation region of the ISM and the diffuse neutral gas. It is associated with the star formation rate and the metallicity, which is found consistent with the local low metallicity dwarf galaxies. In our framework, we find a total 48 C+ bright events, out of which 32 are further detectable by LISA. The far-infrared luminosity, which we calculated, is directly connected to the dust continuum and is used as a tracer of the ISM. So in our model, we find a total of 37 far-infrared bright events, out of which 21 are associated with LISA detectable events. So to put it in perspective, out of 56 total events which could be associated with the host galaxy, 40 events are LISA detectable, and out of these LISA detectable events, 10 events are bright in UV, X-ray, far-infrared, and C+ bands. That is 20% of all LISA detected events should be good candidates for follow-up EM observation within the scope of simulations.
We're running out of time, so would you be able to wrap
Oh,
up?
sorry. So I'll just quickly wrap up. Here I just basically show the electromagnetic facilities, which has the potential to be contemporary to LISA. And finally, just to give the big plot, it's basically the simulated UVFIR and the X-ray maps of the selected events from our simulations that we would expect to see through eligible telescopes, which is done by a Monte Carlo-based radiative transfer code SCRT. And we should basically show a panoramic view of the LISA detected gravitational wave events, And to quickly summarize, we saw that different AGN feedback models can be compared in the direct collapse black hole formation scenario on the merger rates of the massive black hole binaries, as well as the several gravitational wave observables. Keeping a threshold of LISA detectability at 5, we find the angular resolution of most of the LISA events to be quite poor. And upon relating the merger events with their host galaxies and exploring the possibility of different electromagnetic facilities to observe post-merger galaxy, we present a panoramic view of gravitational wave events and its post-merger scenario. So the key point is the post-spatial localization of these events makes association of gravitational wave and electromagnetic counterparts extremely challenging. Sorry for going over time. Thanks.
Thank you. There's a question on the chat which you can address, but I encourage you to follow up afterwards, as usual. So we'll move on to the final talk. I apologize for the late start. So this is Sweda Nassim on Zoom, aligning nucleus crystal in accretion disk. If you can share your screen.
Hi, can you hear me? Awesome. Okay, just give me one sec to get my slides up.
Oh, we haven't seen your slides yet. I don't know if you're sharing already. Yeah, that looks good.
Can you see my screen now? Awesome. Sorry about that. Okay. Hello, everyone. My name is Saida Nassim. I'm a graduate student at the Missouri University of Science and Technology and a visiting scientist at the American Museum of Natural History. And today's talk is about how AGN accretion disks interact with nuclear star cluster orbits, and in particular, inclined nuclear star cluster orbits. In fact, this talk is based on a paper that's also an upcoming paper. So if anyone's interested in this topic, keep an eye out for the release on arXiv, hopefully in the near future. Okay, so nuclear star clusters, I assume we're all aware, have various types of objects from stars and stellar remnants of varying masses, mass distributions, as well as different orbit distributions as far as their inclinations and semi-major axes and whatnot go, and ellipticities and whatnot. And for the purposes of our study, we consider circular orbits for both stars, for various star types and various masses for stellar mass black holes. So what we have here is a little bit of a schematic depiction of what an inclined orbiter's orbital plane in blue, what it looks like when it's crossing through a disk or when it's passing through a disk, which is depicted in gray. So it's essentially, are you guys able to see my mouse by any chance? Okay, cool. So it's essentially the part that's depicted here in black, the arc length that's passing through the disk is where we expect that these objects will experience drag forces. Depending on the type of object, that will determine which type of drag force that it's experiencing. So for stars versus black holes, for stars, we expect most star types will experience a geometric drag force, which is sort of akin to what a beach ball might feel on a windy day. It's a very physical interaction with, well, they're both physical interactions. It's a very direct interaction with the surface of the star versus Bondi-Hoyle-Littleton drag, which we expect for more compact objects. So for our study, we consider a few different masses of stellar mass black holes, but we also expect in principle for compact stars like neutron stars or white dwarfs might also experience Bondi-Hoyle-Littleton like forces. So the key differences between the drag force, the geometric drag force and the Bondi-Hoyle-Littleton drag forces that we are considering are their dependencies on the relative velocity of the orbiter. So the geometric drag being directly proportional to the relative velocity squared versus the Bonduhu-Littleton being inversely related to the same quantity. So this will have an impact on our later results on the time scales for how long it takes for an inclined orbit to be captured within the disk. So as the object is passing through the disk and experiencing these drag forces, it will experience its inclination, the orbit's inclination and semi-major axis will decay until eventually its orientation has become such that it's embedded within the accretion disk given enough time. So we're interested in seeing whether these timescales coincide within the expected lifetime of AGN or not, because this will help us to understand sort of the population of these nuclear star cluster objects within the AGN disk itself. Okay, so as far as capture time being how long it takes for this to happen, we have two different methods for how we calculate this. One being a very direct analytical approximation versus another method, which is a little bit more robust through numerical integration. So when using the analytical approximation method, for the sake of having a faster estimate sort of, or like a preliminary estimate of what capture time should look like, we assume a constant semi-major axis. And I should also mention that we consider circular orbits. So we assume a constant semi-major axis for these analytical approximations, which sort of allows us to, because we assume that they're constant radii, we can sort of calculate how many orbits that the object will need to pass through the disk in order for its orbit to become aligned with the disk. And we can simply multiply the number of orbits by essentially the time per orbit, which will be the same if the semi-major axis is the same. So it's a very fast way to calculate the capture time, but and also it gives us a reasonable upper limit for the capture time. But because we're forcing the semi-major axis to stay the same, it doesn't allow for conservation of energy, which is why we have developed a numerical integration approach, which does allow for the conservation of energy, because for each pass through the disk, we not only calculate how much the inclination is changing, but also how much the object is sort of migrating towards the central SMBH. So since we're calculating this for every single pass through the disk, which is twice per orbit, 2n means 2 times the total number of orbits needed to pass through the disk. Sorry if I'm rushing a bit through things. If there are questions towards the end, I'd like to have a little bit of time for that. Okay, sorry. Okay, so on to results. For stars, so for capture times for stars, what we have here on the top panels represent capture times with respect to initial inclination. So first of all, the gray bands represent a plausible range of AGN lifetime, anywhere from 10 to the 5 to 10 to the 8 years, which is like 0.1 to 100 mega years. It's a pretty big range. But yeah, so anything that is, any data that you see that's above these gray bands essentially means that it's the time scales for capturing these objects is too large, because it surpasses the expected lifetime of AGN. So it's unphysical to expect, for example, these, like this stuff to actually be captured. Anything that's less than it or within the band is a reasonable expectation for things to be captured. So we look at 3 star types, M stars, G stars, and O stars. And what we find is that for denser star types, that the timescales for their capture are consistently larger. and from our analytical approximations, we expected that there wouldn't be a very significant dependency on the initial inclination of these orbits. So from the top panels, the solid lines are what represent our analytical approximations for capture time. Same thing actually in all of the plots. The solid lines are analytical approximations and everything else is data with respect to the numerical integration data for the same initial conditions. So the top panels are with respect to initial inclination and the bottom panels are with respect to initial semi-major axis. So and we also look at two disk models, SG and TQM, which refers to Circo and Goodman and Thomson, Quarter and Murray, which are on the left-hand side and right-hand side respectively. So comparing between two disk models in general, we find that the Circo and Goodman disk is more efficient in capturing objects within AGN lifetime or at all. And Thomson Quarter and Murray disk takes significantly longer. So we don't expect as many objects from these nuclear star clusters to be captured within TQM type disks, at least not as much as compared to SG type disks. One thing that we found that was interesting is that when we look at the numerical integration approach, we start to see a more obvious dependency on the initial inclination. We find that across disk models and across different star types, that the lower your initial inclination is, lower corresponding to like low prograde inclination, the more it converges towards the upper limit from the analytical approximation. But as you increase the initial inclination towards more polar orbits, which are here at 90 degrees, and then more so towards low retrograde inclinations, you start to see the capture time approximations based on numerical integration. It starts to diverge from the analytical approximations. And the reason for this, if we recall for a moment from our previous slide where the key differences between our analytical approximation and our numerical integration approach is that in our analytical approximation, we keep the radius constant, but when numerically integrating, we allow for the radius to change. And it's because we allow for the radius to change when the object is migrating, as the object is migrating over capture, that is what allows for it to move towards denser regions of the disk as it moves inward, and that makes the capture time more efficient. So on the bottom panels, what we have here in the first and second are essentially looking at how the capture time for these three different star types, how it compares for an initial inclination of 45 degrees, which is a prograde inclination, and an initial inclination of 135 degrees, which is the same inclination, but in retrograde orientation. And what we see is the analytical approximations are actually the same in both cases, but in the 135 degree inclination case, we find that the capture times are a little bit better. And also we find that the object migrates a lot more. So the star symbols, I should say, are what represent the actual capture times, and the X symbols sort of represent, for the same capture times, the final semi-major axis with respect to the initial semi-major axis. And we see the same behavior in both disk models. Yeah, okay, so moving on to capture time for SPH. This gets a little bit messy, but maybe I can do a little bit better with explaining this. So we look at two different masses for SPH. Now the key difference, the structure of these plots are essentially the same as the previous, except that now we look at a 10 solar mass SPH as well as a 50 solar mass SPH. And now each of these objects have their own rows of plots. And the colors now correspond, instead of two different objects, now they correspond to different initial conditions. So now we are looking at, in this top figure, capture times with respect to inclination, and the colors correspond to their initial radii. And for various initial radii, when we compare these two SPH masses, we actually find that for higher mass SPH, the capture times are slightly more efficient. The behavior is essentially identical as far as which regions of the disk are more efficient for orbit capture. It's simply that the time scales that are sort of offset from each other. And in the bottom panels, again, we have capture time with respect to initial semi-major axis, and now it's colored by a range of initial inclinations. And again, the SG model are the left-hand half of the plots, and the TQM models are the right-hand half of the plots. So in this case, the green panels for each respective model correspond to initially prograde inclinations, and the red panels correspond to initially retrograde inclinations. So what we're finding so far is that in the case of SPH, for initially prograde orientations, for initially prograde inclinations, we see significant migration. And I use the term migration lightly because this is happening as over the course of capture time, not while these objects are already embedded in the disk. So essentially migration here is defined as the total change in semi-major axis. So from the start to finish, we find that like for prograde, initially prograde conditions, there's more significant migration versus for initially retrograde inclinations. We don't see as much of a change in radius. So it's sort of the opposite behavior as to stars. And if we go back up to the upper panels for just a second, an easy to spot one perhaps would be like looking at the topmost set of triangular points we have here with respect to this same colored solid line. We can see that, we can see that for initially low prograde inclinations, it has diverged more from the analytical approximation versus for initially low retrograde orientations, it starts to converge more towards the analytical approximation. And what I mean by this is, like when we looked at stars, we see a bigger gap in the two different methods at high inclinations towards 180, but a smaller gap towards 0, versus for SPH, it's the opposite. As you get closer to 180, you see a smaller gap, versus when you get closer towards 0, the gap widens.
A little short, so would you better?
I'm sorry, I didn't catch that.
We're running out of time, so
okay.
If you'd be able to get to your summary, please. Sorry.
No problem. Okay, sorry. Okay, so this will be my last slide. just looking at the sort of evolution sort of summarized for a representative star type and a representative SPH. So we're looking at O stars and 50 solar mass SPH, and they each correspond to their own rows. And again, on the left-hand side is with respect to the SG model, and on the right-hand side is with respect to the TQM model for the accretion disks. And essentially what we're looking at here is how the inclination and semi-major axis of various initial conditions for these objects, how they change over the course of capture time. So in this case, all of these orbits are starting with an initial radius of 10 to the 4 RG. And the color is showing us how the radius is changing with time. And again, the gray bands are with respect to the age and lifetime, and the plots themselves, like the lines themselves, are showing us how the inclination is changing. And an interesting behavior that's a little bit more obvious here than in the previous plots are that for stars in these top panels, we find that they, like, irrespective of what your initial conditions are, they always evolve. The inclination always evolves to be more prograde, even if it doesn't actually get all the way, even if it's not all the way embedded in the disk by the time that it's captured. It's moving down towards a smaller inclination or towards a prograde inclination, versus for SPH, there is sort of a line where at 120 degrees or higher, they won't be flipping towards prograde orientations. They will be embedded in retrograde orientations. And anything less than 120 degrees will be captured with prograde orientation. And that's a bit rushed, and I'm sorry for that. But if anyone has any questions, I'm happy to answer, and hopefully there will be a lot more detail in the upcoming paper. Thank you for your time.
Thank you for the nice talk. I encourage questions to happen in the discussion sessions or offline. So is there any announcements?
So I just posted in the chat the link again to the discussion thing. So if there's any questions that we couldn't get to, please go to that link and you can add your questions or discussion point for this afternoon. So that's all.
I don't know. We were thinking maybe to take a group picture where everybody on Zoom turns on the camera. We post them on the wall and we stand in front of the wall. I don't know if people are interested in doing that. And then we send it to the Lisa social media team and post it on social media stuff. I don't know. Are people up for that?
Yes.
Yeah.
Okay. The cameras are turning on already. Thank you.
So we,
great.
Can you,
So
okay, so people maybe
and then can we,
yeah, we can also take a screenshot.
and can we post it here on the wall? Like the,
Yeah.
Somebody to take a picture.
Yeah, I guess.
No, you have to be on the picture. You are the main organizer. So everybody turn on your. Oh yeah, see the
It's also should be quick because people are leaving.
Yeah, I was wondering if you
So I think, we're gonna have to.
Yeah.
So this is a pre-photo. And then we will have.
So 10 seconds.
But do you want to be?
This should work.
Wow.
Oh my God, 7 seconds. 7 seconds. 6.
Hurry,
Four. 5. I don't know. 2. 1. Don't move.
Don't move.
Too late.
Don't move people in the videos.
It's okay.
Okay.
Thank you. It's a picture. See you also a picture at least.
Thanks to all.
There's something in it.
Okay, thank you, everyone. See you this afternoon.
Bye.
Lydia, I sent it to you by email. Right.
You don't have my number.
No, your email. I sent it.
Email.
Ah,